Hello, guys. Welcome to today's topic. We're gonna continue today with the subtopic of the lever, part two, in which we're gonna get into the introduction of the second and the third class levers, and we're gonna solve two problems concerning these classes of levers. Remember that last time we only saw what the definition of lever was, what the equation for the lever was, and also the first class lever. So let's go on. So like I was saying, we know up to this point that there are three classes of levers: the first class, the second class, and the third class. And the only difference between them is the relative placing of the fulcrum, the effort, and the load. Remember that I told you about these mnemonics that can help you in order to understand, in order to memorize what class corresponds to what placing. So, for example, we have this phrase: Ethel is an elf that fell down, and these three words, the name of the elf, the word elf, and the verb or the action, um, stand for each class. Okay, this is the first class because you have first the effort, then the fulcrum, and then the load. You have the second class, which is effort, and then load, and then fulcrum, and then you have the third class, which involves first the fulcrum, then the effort, and finally the load. So you only have to memorize this thing and you're set. Okay, so what is the second class lever? It's effort, load, and fulcrum. So let me draw that. We have the fulcrum at the end, then we have the load over here. Okay, fulcrum, load, and then we have the effort in this way. Okay, so let's suppose we are raising the load. I'm applying an effort upwards and I'm raising the load upwards, and we have the fulcrum in here, which is actually one of the best applications of these types of levers. Okay, like this in a wheelbarrow, which is the same thing I drew a moment ago. You have the fulcrum. Okay, oops, sorry, which is this place. This is the fulcrum. Then you have the load, and then you have the effort. Okay, and what are the applications or the advantages of this type of lever? Well, the classic or the most important advantage is that it always offers amplification of the input force. Remember, the input force is this, the effort. And since the effort arm, remember the effort arm is the distance between the fulcrum or from the fulcrum to the effort. This is the effort arm. So since the effort arm is always greater than the load arm, which is this little bit, okay, for this type of lever, for second class lever, you will always have that the effort arm is greater than the load arm. Why? Because the load has to be placed somewhere in here, okay? So it doesn't matter where you place it, it's always going to be less than the effort arm. Can you see that? I mean, if you place the load up until this point, they would be equal. But that's the extreme case, okay? In most cases, the load will be in between the fulcrum and the effort, and so the effort arm will always be greater than the load arm. And that guarantees to you that you will always have an amplification of the input force. Now the third class lever, we have FEL, fulcrum, effort, and then load. So let's draw it very quickly. We have fulcrum, then effort, and then the load. Okay, like so. So what are the applications of this type of lever? We have, for example, two applications. One which is that it can speed up a task, and the second is that it can reduce the input force or the effort. Remember, the input force is known as the effort. And in some circumstances, this is actually desirable to reduce the input force. I'm going to talk about these two right now. Well, first this first one, okay? What do I mean by this lever, the third class lever, being able to speed up a task. Okay, let me show you a short clip of a video in YouTube. Okay, look at this. We have a robotic arm here. I'm sure you have seen these type of things. Okay, so suppose that you want this arm for raising things from the ground to a certain height, like in this way. Look, like that. Okay, that's the only thing you want this robot to do, to raise something like that from the ground to a certain height. Okay, now what I want you to look at is the speed of this robot, of this arm. Look at the speed. It's constant, and it's something that we could say that it's quite slow, right? Many of these robot arms actually operate at slow speeds like that. Constant low speeds. Okay, can you see that? So suppose you want this robot to raise objects from the, like I said, from the ground to a certain height, but you need this robot to do it faster. Okay, for some reason you need to do it faster, but you cannot program this robot to actually go faster because this is built in. Okay, the velocity of this object is built in, which means that you cannot change it. So what can you do in order to perform this task of raising something, let's say from this point to this point, faster with this robot? Well, what you can do is use a third class lever, like I'm going to show you here. Okay, look at this video. So this is me, and I'm going to play the role of that robotic arm. So let's see what I'm doing from the beginning. Pay attention. So yeah, that's Woody, and I'm placing Woody. I'm attaching it to the extreme of this lever. Okay. Why do I say that this is a lever? Well, easy. This is a rigid bar. Well, it's not so rigid, but it's approximately rigid. Okay, so we have a rigid bar, and we have the other requirement. We have a fulcrum. In a moment, you will see that this arm, my right arm, remains fixed during the whole experiment. So this plays the role of the fulcrum. Okay, so we have the fulcrum, we have the rigid bar. What else do we need? The effort, which is going to be applied by my left arm, and then we have the load at the other extreme of the lever. Now, suppose that I'm not here, okay? What I want you to understand is that we're talking about the robot a moment ago, and let's suppose that my arm, this arm, is actually the arm of the robot, okay? So let's see what happens when you actually um, put the robot to work. Look at that. Look at this. The robot's racing the arm. Can you see that? And look at the relative speeds between the arm and Woody. Look at the relative speeds. Can you see that? It's simple. Look, when the arm went, I'm gonna choose yellow. When this arm went from this point to this point in a certain amount of time, Woody went from this point to this higher point in the same amount of time. Okay, so you are actually raising an object with the robotic arm faster than it would have taken if you put Woody at this point in the robot. Can you see that? Because the speeds are different. This arm is going from here to here in, say, 1 second. Okay, let's say it took me 1 second to go from here to here, and Woody took the same time to go from here to a greater height. So obviously Woody is moving at a greater speed or velocity than the robotic arm. Okay, the robotic arm is not moving quickly, but Woody is. So in fact, you can just uh, change the velocity at which you perform this task of raising an object by matching or coupling the robot with a third class lever. Okay, it's simple to understand. Let me play it one more time so you can observe it. It's quite simple. Okay, this is extremely simple physics, but it works. Look at that. Look at the relative velocities. Okay, and all of that with just a simple rigid bar. It's simple physics. Okay. Okay, so that's what I meant by speeding up a task. And in a moment, I'm going to tell you how this third class lever can also help you reduce the input force. Okay, so let's go straight to the examples. Take pencil and paper and calculator, and we're going to perform two examples in order for you to go into the activity in a moment. Okay, so the example number one says the following: a bottle opener is used to open a soda as shown. Okay, so right here I am with a bottle opener. I have a soda, and that's it. Okay, that's the context. And we have the necessary force for the cap, which is the corcholata, to give in is 7 newtons. So the force that you have to apply on the cap right here, you have to understand this. The bottle opener applies the force at this point, okay, and it does so upwards. This is where the force is going to be applied on the cap. And you have to understand also this, that this little part of the bottle opener doesn't move that much. So this is actually the fulcrum. This part is the fulcrum. Okay, obviously this point in here is the effort, is where my effort is going to be applied in this direction. Okay, and what do you think this is? This is going to be the load, right? The load or the output force. So what type of class do we have here? What type of lever? I don't know what I said, sorry. What type of lever is the bottle opener? We have fulcrum, load, and effort. Or if you read it backwards, we have effort, load, and fulcrum. I'm going to write that down. Effort, load, fulcrum, ELF. Okay, so this is a second class lever. So let's see how this works. The problem, it says the effort arm is 12 centimeters. Let's see what is the effort arm in here. Remember, the effort arm is the distance that goes from the fulcrum to the effort. So all of this is in fact 12 centimeters. And let's keep on reading. And the load arm is 2 centimeters. The load arm is the distance from the fulcrum to the load. So this little part in here is 2 centimeters. Okay. All right. So we have all the effort. We have all the information to calculate the effort that we need to apply on the extreme of the bottle opener in order to open the cap. Okay. So let's see. What is the fundamental equation for the lever? Remember, it's effort times effort arm equals load times load arm. Ella. You can memorize it that way. So let's put all the information we have in here. The effort, we don't know it. That's what we're trying to get. The effort arm is 12 centimeters. The load is 7 newtons. That's the load we have to apply in order to open the bottle. And that's right here, 7 newtons. This verb, I don't know if you know it, giving in means vencerse. En español esto se diría, la fuerza necesaria para que la corcholata se venza es 7 newtons. Okay, now the load arm. The load arm, as we said, is 2 centimeters. And that's it. Okay, now we just have a mathematical problem. It's no longer physics, it's just mathematics. So let's isolate the effort. It's gonna be 7 newtons times 2 centimeters over 12 centimeters. Okay, take your calculator, calculate this number, and we will get 1.16 newtons. Okay, centimeters cancels centimeters. You don't have to convert to meters in this case because in the end they will be canceled. But technically, that's the best way to um, to do it. Okay, you have to convert centimeters to meters always. But in this case, it doesn't make any difference. Okay, so this is the effort needed to open up the bottle. Okay, so as you can see, it's less than the necessary force to apply to open the cap. Okay, why? Because we are using a lever, and remember, levers help you apply less effort to do a certain task. Okay, if you put your effort right in this at this point, you would need 7 newtons right at this point, but since you're applying it at this other point, you have to apply less. You can do it with less effort, with less force. That's the advantage of levers. Okay. Okay, let's move on to the last example, example number 2. We have the following. This is an example of a reduction of the input force. You will see in a moment. So let's read. It says a pair of 10 centimeters tweezers are used to pick up a small fragile insect. And this is the context, okay? I didn't find something to play the insect, so I pick up just a little frog that I had in here. And these are supposed to be the tweezers, okay? But these are prongs for carne asada and stuff like that. Okay, so, but it's the same, right? So an effort of 0. newtons is applied 2 centimeters from the fulcrum. So let's draw that. Let's draw right away that thing. An effort of 0. newtons. Where is the effort being applied here? At these points, right? By my fingers. My fingers are applying the effort on the tweezers at this point, and that effort, we are told, is 0.1 newtons, which is a very small force, okay? And it's applied 2 centimeters from the fulcrum. What is the fulcrum in this lever? It's right here. This is the point that doesn't move at all when you play with these things. Okay, so this is the fulcrum, and so the uh, the effort arm will be this, because this is my effort, this is the fulcrum, so this is the effort arm. So we have that the effort arm is 2 centimeters. Okay, okay, let's go on reading. How much output force or load is being applied on the insect? So when I apply this effort of 0.1 newtons right here at this point, what's going to happen over here where the load or the output force is going to be applied on the insect? Remember that the insect is very fragile, it's very small, so we cannot apply a lot of force on this thing. We need less force than the one we are applying. We're applying this much force, and let's see how much force is coming out of this point in the tweezers. Okay? Okay, so how do we find that? We have the load, which we want to find, and so we must need the load arm. What is the load arm? It's the distance from the fulcrum to the load. Okay, it's all of this. So look at here in the problem. Where can we get that information, the load arm? Can you see it? It's gonna be this, right? It's gonna be the whole length of the tweezers. Can you see? Look at the diagram. The load arm is in fact the whole length of the tweezers. So that's going to be 10 centimeters, like this. And we have everything in order to calculate the load, because we have all the information. We have this, we have this, we have this, and with our equation we can find the load. So let's write down the equation. Effort times effort arm equals load times load arm. Let's substitute everything. 0.1 newtons times the effort arm equals the load times the load arm, which is this. I'm gonna go over here now. So I'm gonna divide both sides of that equation over 10. A very simple algebraical step. Over 10 centimeters, I meant. Okay, and that's gonna be equal to the load. So let's calculate this value, guys, please. Okay, and we're gonna get that the load in the end is going to be equal to 0.02. Okay, 0.02 newtons, like that. So this is the answer. So this is the force that is being applied on the insect at the other extreme of the tweezers. Okay, I'm applying right here at this point a force of 0. Newtons, which is quite small. I'm being very gentle on this insect, but that force, which is already gentle, is being reduced even more. Look, 0.02 newtons, even more, so that you don't kill this thing. Okay, so that's how you can reduce your input force, by using a third class lever. I didn't mention that. Okay, this is a third class lever. Why? Because we have, I'm gonna do it in blue, we have fulcrum and then effort. I'm gonna write it down. Fulcrum, effort, and then the load. Okay, and whether you read it backwards or in the normal way, it doesn't make any difference. Okay, so this is fell, and remember that that's the last word on that phrase. Fell down. Okay, so this is a third class lever. Third class levers help you reduce your input force. Okay, so that's it, guys. That was the end of the class. I hope you have enjoyed it, and now we can pass to the activity. Thank you.